Hello grade 12s. This video is in response to a question originating from this picture, and that is explaining how the partial hybridization works around ethene. So let's dive in. Alright, so the Lewis structure for ethene is right here, and to explain how these bonds are created, we have to look at the individual bonds between carbon and hydrogen here and here, also between carbon and carbon. Okay, and in doing that, we're going to explain also how what happens here. So let's start with looking at carbon's ground orbital diagrams. So carbon's ground state looks like this. And again, we're only looking at the valence electrons in carbon, so 2s and the 2p's, 2px, 2py, and 2pz. And they look like this. Carbon has 1, 2, 3, 4 valence electrons. We can see here that carbon needs 1, 2, 3, 4 half-filled suborbitals. It doesn't have, in this case, 4 half-filled suborbitals, so we promote an electron as we have seen before. So in its excited state, carbon will see this promotion occurring. So we'll have this electron move into the 2pz empty suborbital to then look like this. 1, 2, 3 in 2px, 2py, 2pz, half, half, and half. Good, so we have 4 half-filled suborbitals, and this is now ready to begin hybridization. Now, this is the part that we have to pay attention to when we're looking at double bonds. We need a sigma bond. Okay, between this carbon and this hydrogen, we need a sigma bond, so this has to be a hybridized suborbital that will overlap, directly overlap or head-on collide with hydrogen here, carbon and hydrogen. And the same thing happens here. We need a hybridized half-filled suborbitals, that suborbital that will occur between this carbon and this hydrogen. Between the carbons, we have a sigma and we have a pi. Right, in this pi orbital, we know that it's going to consist of an unhybridized p orbital, whereas a sigma requires a hybridized state. So we have 1, 2, 3 hybridized states and 1 unhybridized one. So that means our partially hybridized carbon atom's electrons will look like this, where we have 1, 2, 3, right? 1, 2, 3 electrons forming these sigma bonds. So that means we have an s and 2 p's, which gives us an sp2 hybridized state around this carbon. Similarly, or actually exactly the same, is happening on this other end over here. So we can repeat all of this again for the second carbon. I'm going through the details of one, and I'll just draw the partially hybridized state to the side over here, showing you that this happens as well with the other carbon. Okay, we're forgetting something. So on the second, rather the last electron is our unhybridized 2pz. Okay, so that's now the partially hybridized state, including a hybridized 1, 2, 3 electrons, creating your sp2 hybridized states and a 2pz. Now this is exactly the same for the second carbon. Maybe we can even call this carbon 1. And we can call this carbon 2. Okay, so the partially hybridized state is exactly the same. So 1, 2, 3, and then a 2pz, and this is sp2. Okay, now let's see exactly how this question isn't asking you, or I guess you don't need to see what I'm going to show you now, but I think it helps to understand what's happening with the hydrogens and with carbons, and see how all of this comes together. So again, we have one carbon here, we have one carbon here. Let's figure out how these carbons bond together with the hydrogens. Let's draw hydrogens off to the side here. So this one carbon 1 has two hydrogens, and this other carbon has 2 hydrogens. So let's draw these hydrogens. We have 1, 2, so these are all our hydrogens. We have 1s, 1s. Its electron here on this side, we also have 2 hydrogens, right? 1, 2. We have 1s, 1s, and their electrons. Now these sigma bonds occur here between this hydrogen and that hybridized suborbital, and here as well, right? Now that also occurs here and here. Now this isn't completely done. We have to change the spin of our electrons, right? But let's do that at the end. So those are our sigma bonds. Now there's another sigma bond that occurs between each of the carbons. So let's go ahead and draw that. So this is one carbon, that's the other. Now ahead of time, I'm apologizing. This is going to look a bit messy, but we have this hybridized suborbital. Let's just draw it like that so I don't overlap too much. Right. Head-on colliding with this electron. Okay, so we have, just clear this up a little bit. I'm going to redraw that. That's slightly better. Okay, so we have a sigma bond between carbon and carbon, a sigma bond here between carbon and hydrogen, sigma bond here between carbon and hydrogen, and another sigma bond here between another carbon and hydrogen, another one right there. Okay, now before I continue, I don't like leaving it like this. I'm going to just change the spins on these electrons, right? Instead of them both being spin up, this is now going to be spin down, this is going to be spin down, and spin down. Okay, good. Last but not least, we have our hybridized, or rather our unhybridized 2pz orbital, and these have to exist in the same orientation, right? If you recall, not the best drawing, but you get the idea. Here we have our x-axis, our y-axis, and our z-axis. What we're looking at is, and again, these two can be drawn differently. They can be switched around. You'll see both versions online or in other textbooks. So this p orbital, roughly, has to be completely, or has to be exactly the same as another orientation that will create that pi bond, right? It isn't a head-on collision like these sigmas are between an sp2 hybridized state and a 1s electron from hydrogen. Instead, they overlap, they're parallel to each other, creating that typical kidney bean structure that looks like roughly like this, right? Creating that pi bond. And that's what's happening at the two PZs on here and here. So let's connect these. And again, apologize, it's going to look a bit messy, but hopefully you can make sense of it with these different colors. Okay, so this is where that pi bond forms, and that occurs between these two carbons. Now, like we did with the sigma bonds, one of the electrons have to change orientation. We can pick either one. And this is now spin down. And we're done. So this is how the sigma pi bonds exist inside of ethene between carbon and all the hydrogens in it as well. Hopefully this helps. Post any questions.